So
Uh,
in task one, I actually just share my screen. In task one, you have the UML diagram that you're creating,
yeah.
and then in task two, you're asked to implement those things.
Yes, sir.
Yeah. So, all right. Any questions about the assignment or the course or any of the previous lecture content before we begin?
So for no, sir, I'm ready when you are, sir.
Okay.
I also had one more question, sir.
Go ahead.
In my code, the output for the date of birth line
Yeah.
is CAT, but in the assignment it shows SAST. Is that okay?
Yeah, that's fine. So what the date utility does in Java is it tries to localize it. So it will use the date. It'll interpret the date according to whatever time zone you have set, or like
Okay,
your
sir.
computer's date time. Yeah.
Okay.
All right. So let's get started. Unless there are other questions or comments. No? No questions, no comments? Okay. Just give me a second here.
Sir, sorry, sir,
Yeah?
just before the assignment demo, I obviously commented out first
Yeah.
and uncommented, yeah.
Yeah, that's fine. Yeah. Um, because the assignment demos are actually just for you to kind of have an idea of what if it's working early on. But you should be doing extensive testing on your own program and making sure everything's correct.
Yes, sir.
All right. So today we're gonna quickly recap UML diagrams. I was actually going to draw everything, but it seems like my tablet doesn't want to work properly. We'll see how I fare with the mouse. But we're going to recap quickly interfaces and abstract classes, which abstract classes you're using in this assignment 4, and UML diagrams. And then we'll briefly talk about something called generics. The generics is not going to be testable, but it is an interesting part of the Java type system, and I thought I would share it with you. Tomorrow we won't have a lecture because it's Tuesday, and on Wednesday we'll talk about kind of where you can go with Java from here. Talk about various aspects like game development or web programming. We'll talk about testing and debugging Java programs, but it's much less formal. And then on Thursday, we'll start with a review, because next week, Thursday, you have your second test for the COS101 second semester. So we'll start to review this week, Thursday, and we'll have a review Thursday, Friday, Monday, Wednesday, and then Thursday the test starts. Is everyone okay with that plan?
Oh, excuse me, sir, you said that we're going to have next week, we're going to have a session Monday, Wednesday,
Yeah.
and Thursday before the test starts.
Yeah, so Thursday at noon, the test will start. So we'll have Monday and Wednesday as recap sessions.
Yes. Is the same going for this Friday, sir?
Same for this Friday. We'll do a consultation session where you can ask me questions, but I'll be recapping the Java stuff. Yeah.
Yes, sir.
All right.
So,
Yes, go ahead.
so does this mean we're done with everything that we're going to be tested on?
Yes. So up until abstract classes,
Yes.
everything before abstract classes you can be tested on, including term 3. So if we ask you to create, an array, or if we ask you to do for loops, while loops, you should be able to do them. And then we'll also test, object-oriented programming, interfaces, abstract classes, and inheritance, as well as polymorphism. Okay.
Okay, so
All right. So when I do the test announcement, it'll be, the test announcement should come out on Thursday. I'll detail everything that is examinable in the test. Okay. All right, so moving forward, we're going to do a brief recap about last week's work, and then we're going to talk about UML diagrams. I was hoping to make it a bit more interactive and draw them for you. I'm not sure why my tablet's not working properly, but we'll see how well we fare. And then we'll talk about generics. UML diagrams are testable, generics are not. So in the test, you might get a UML diagram, and then we ask you questions about it, but we won't ask you questions about generics. All right, so we made a distinction between something called a class interface with a lowercase I and a Java interface with a capital I. A class interface is something that is related to object-oriented programming in general, not just Java. And a class interface is all the public methods, variables, and constants that you can use to interact with the object. All right. So you can imagine like a program. There might be a whole bunch of code running in the background, or a computer. There's a whole bunch of complicated things happening in the background. But you, the user, are able to use an interface, like a keyboard and a mouse, to interact with a very complicated system. In the same way, classes have an interface, and that's what's used to interact with them. So the public methods, the variables, and the constants, that's what we work with. A Java interface is a way for Java to implement something called multiple inheritance, or because our rule is that in Java, you can only extend one class at a time. So we have single inheritance. And so Java says, okay, but what if you have unrelated classes that need a shared set of methods? That is why Java uses Java interfaces, so capital I. And a Java interface is essentially kind of like a piece of source code that describes a set of public methods to be implemented. Okay, so the implements keyword is what we use when we want to say, look, this class uses this interface. And if it uses that interface, we know it has these methods implemented. Okay, so the keyword is implements. Actually, let's go over here. So a class implements an interface, right? If we took say like our class name implements interface. All right. That means we are overriding all of the methods described in the interface. Overriding. Okay, so overriding, not overloading. Right, be careful in your test. The Java interface can also be treated as a type, right? So if you have like a parameter to a method, or like a collection, an array list, right? You can use an interface as if it were a type, and that's because Java at compile time can figure out if an object has like the method related to the interface, right? So they all share the same public methods, which is why we can use it as a type. Something I forgot to add to the slide is that with a Java interface, it is only public methods. You're not describing any variables or private methods or anything. It's just public methods. Okay, so an interface just is a recipe for public methods. Then we looked at how you can take an interface and you can use the extends keyword to make more specialized interfaces, right? So there is inheritance for interfaces. So if we have an interface, we can inherit from another interface, right? So this interface inherits from this one. And if the same way that if we have a class, we can extend that class with another class. So the bottom class extends the top class. However, we may not have a class extending an interface or an interface extending a class. That's not right, right? A class implements an interface. A class can extend a class, and an interface can extend an interface. Okay. Those are the three rules we have in Java. Right. Then we had this idea of an abstract class, which is like a special Java class that its only purpose is to serve as an ancestor or a blueprint class for related types, right? We never instantiate an abstract class. In fact, it is illegal to do so. So it is never instantiated. We don't go new, we don't use the new keyword on our abstract class. The reason for this is more on the kind of mental modeling section, where we might have a type that needs to be generic enough, but is actually not a usable class. It's just kind of there to provide a blueprint or a skeleton for more specialized classes. And it's also there so that we can group those more specialized classes together under the same umbrella. And when we group different types of classes under the same umbrella or category as the superclass or an ancestor class, that is an example of polymorphism, right? Treating a type of one class, right, an object of a specific type, as one of its ancestor types or possibly its interfaces that it implements, right? So that's the idea of polymorphism. Then within abstract classes, we had this concept of abstract methods. And an abstract method is a method with no body that must be implemented and read there overridden in the subclass. Okay, and I use the word implemented here to make you think of interfaces where an abstract class, if we had some sort of abstract class, can have multiple abstract methods, and then it is up to the subclasses that might be, you know, a little bit different each, but they all have to implement those methods. Okay, so it's a way for us to kind of set up a class interface with a small I using an abstract class. All right, so that's it for the recap. Are there any questions about abstract classes, interfaces, polymorphism? Okay, let me just double check. I don't have any comments. I think we're okay. All right. So let's move on to UML class diagrams. UML stands for the Unified Modeling Language. Modeling in the terms of like modeling clay, right? We're trying to put a visual representation of ideas together. It is kind of language agnostic, so whether you're working in C++, you know, Java, Python, the UML language can be used for any of those programming languages to define like a system, to explain a system and to kind of describe it. I think either next year or in third year, you'll end up doing software architecture or software design, where you work on things like architecture diagrams, sequence diagrams, activity diagrams, and class diagrams. So class diagrams is a category of UML diagrams. There are a whole bunch of tools for drawing UML diagrams. At the top of my list personally is Plant UML. Plant UML has like its own little syntax language that you can use to write the diagrams. And they're related, so you define what's in your diagram and what the relationships are, and then it figures out the layout for you. It's quite nice. You can also use tools like Google Drawings, Inkscape, Visual Paradigm, I think even Figma. The UML language, the UML diagrams, is actually just a set of rules, so you can use anything, and as long as you adhere to the rules, then anyone can read your diagrams and understand how to implement it. So I'm going to draw some. Yes, go ahead.
Out of all of your options, the plant one is like, I feel like that's the best one, because the Google one, you have to do everything from scratch. Like you have to make the block and make the circle, whereas the plant like does it for you just by you adding their own code.
Yeah, exactly. So I was hoping I would have my stylus working today, but we're going to work together and draw a class diagram, a couple of class diagrams together. All right, so with any UML class diagram, you start off with a square or a rectangle, and it has 3 main sections, right? So does anyone want to answer what goes in the first section up here?
Isn't that your class?
Yeah, so this is the class name. And typically when you use plant UML, it'll put a little C in a circle for you. Other things that are correct are to say class, like actually just write out the word class, and then the name of the class. Okay. Then
Basically, your attributes and methods, if I'm correct.
Yeah, so then you separate it. And next is the attributes. So these are attributes. I'll just put that like that. And these are the methods. You don't include these labels, but I'm just dividing up the sections for you. So the class name goes up here, then your attributes go over here. So if you are writing your class diagrams, remember that you have to communicate in a way that is usable not just in Java, but in Python and C++ and so on. So oftentimes we will put a plus if it is publicly accessible, right? So if it's accessible outside of the class, we will have a minus if it is accessible only inside the class, so private. And I think square is protected. I'm not 100% sure. I'll have to double check for you. So then you have the plus or minus. So this is the access type, right? So the access. And if you recall, access modifiers are related to encapsulation. So any language that has decent object-oriented programming implemented will have some sort of idea of access to a variable or whatever. In Java and in C++, in Java and C++, we literally have the words private, and public. And in Python, attributes labeled with an underscore, starting with an underscore, are viewed as private. Okay, so that's kind of an interesting fact to know. You have the access, then you would have the name of the attribute. So name, if this was a person, we would have the name of the attribute or the variable, and then you have the type of that attribute. Okay. You don't need to put semicolons. This isn't actually Java, it's just a drawing, so you don't have to put semicolons. Okay, so then you'd have a whole section of attributes and types and so on. And then finally, you would have your methods. So in Java, we call these methods. In more pure object-oriented programming speak, we call them behaviors and attributes. So in Java, we would call these, variables or parameters or arguments or whatever. And in object-oriented speak, we'd say attributes and methods. Okay, so for the methods, we would similarly say it is either a public method or a internal private method. Oftentimes, we don't have private methods listed as part of the UML diagram, just because they're not actually useful in seeing how classes communicate with each other, right? However, internal, the data contained within a class, is relevant no matter what. Okay, so private, public, and protected attributes are all listed. However, public and protected methods are listed. We don't often list private methods. This is because private methods are usually like utility or helper methods, so that we can kind of do things a bit easier and we don't have to repeat ourselves over and over. So we would have our indicator either public or protected, and then in that sense we have the return type. So it'll often be return type first, returns the name of the method, and then the type any parameters or arguments, right? So we do something like this. Some versions of the UML diagram would have us do the access modifier, the name, the parameter list, and then maybe something like this with the return type, right? Something like that. What we're looking for when we're marking your UML diagrams is that it's just clear what the access is of the method, what the name is of the method, any parameters, if at all, and any return types, right? So we can see that this returns that with a parameter list. We can also see that this method takes these parameters and returns that type, right? So these are similar. Don't try to overcomplicate your UML diagrams, please. They're meant to be simple and clear, right? Although these are drawn very horribly. Please excuse my drawing. So let's look at, so this is for a single class, right? We have a single class with a certain name, and that's fine. But class diagrams also show the relationship between different classes. So we have over here, one thing I will note actually before I move on, the reason why we have a class is because you can also model things like packages, like a package or an enum, or whatever, right? So there are different things we can say. In this case, with UML diagrams, we want to say that there are classes. That's why we have the C in a circle, or the actual text that says class, and then the name. All right. So let me just get rid of that. All right. So what happens when we need to show the relationship between UML diagrams or classes, right? So we might have a very complicated system where we have multiple different special classes. We maybe have an abstract class. We have all these different things like interfaces, blah, 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 blah. So we would do something like this, where we'd have, let's take the first example. We have one class that extends another class. So we would draw the UML class diagram of our superclass. We would put a little C there, and we'll call this parent, right, with a P. It would have some attributes and some methods over there. And then we have our other class like this. And we call it, we say it's a class, and it is our child class. And then we have the attributes and methods of the child class. Now, the first thing we need to know is that we don't put, so all of the attributes and methods are inherited by the child. So we don't have to copy and paste the attributes and methods of the parent. However, if these two have an inheritance relationship, we say that the child extends the parent. Okay, and we do a little hollow triangle like this. So a child class extends a parent. It doesn't always have to be up like this, but in our default or most sane version of UML, classes will go up the chain. So you have your most generic classes on the top of the diagram going and specializing down. If we had another child of the parent, we would do exactly the same thing, where we'd have this, and we'd say it's a class, and this is child 2, and this also inherits over here, right, with a hollow triangle. Okay, so this is how we show inheritance. So now we can see, if we just take it at a glance and we see like what's the most generic or like core class to understand, that would be this class over here, right? Because these are all pointing up. So the inheritance, you can imagine like a family tree, right? A family tree is like your parents, and then you might have multiple siblings like this. So the class diagram works a lot like an inheritance family tree, right? And then you'd have just even more beneath that, because people have another. So something like this, right? So we want to go from the most specialized to the least specialized. All right. So if we have inheritance, then we can do things like class A. So say class A is inherited by class B over here. So just pretend this is square. Class B over here, and then you can have like another class down here, class C over there, inherits class B. Okay. So now what we're saying here is that class C, let me just get my red pen, class C is a type of B, and class B is a type of A, but that also means in terms of polymorphism in Java that C is a type of A as well. Okay, but we only point to the direct ancestor. Okay, in the same way that the super keyword only goes up one level, our inheritance arrows only go up to the direct parent. All right. Is everyone okay with that? Any questions?
Right, sir.
Okay. All right, so that's UML diagrams. That's literally just what you need to know. Just remember that it's the name of the class, show that it's a class, all of your attributes with their types, all of your methods with the signatures. Okay, simple as that. And then if you need to show inheritance, it's a little hollow triangle pointing up the inheritance hierarchy.
So in the previous slide for type, you just put in brackets.
So this is like if you have a parameter list. So if we have an argument, we would put the type of the argument and the argument name. Or if we don't have any arguments, just erase that. 1 second. So if we have a class like this, if we don't have any arguments, we can just say the method name, right? The name, and then parentheses like this to show that there are no arguments. Does that make sense?
Okay.
Yeah.
Yes, sir. Yes, sir.
So if we didn't put the parentheses, it might be confusing for someone if we had something like this, where an attribute has a name and a method has a name. Okay. Even though by convention we know attributes go on top, methods go on the bottom, we do this just to distinguish the two. Okay.
Will be a major problem if I don't have the middle line, because in the plant website, I don't have a middle line like our sir has it. Or must I include it?
So let's quickly go to plant UML.
I feel like this is a feature I'm missing.
Yeah, there should be in the class diagram. So you'll see there are 3 sections.
Okay,
you can see this in, yeah. So if we look, they should have an example adding methods. So you put
I just copy my code and put it there and use the way. Okay, I see. So.
Yeah. So you can see here that we have inheritance because we have the hollow triangle. This object has no attributes, but it has a method called equals.
Yes, sir.
Okay. Right, over here you can see the return type is put before and that it has no parameters. And then over here you can see that the attribute has a type put after. And over here you can see that the attribute has a type put before. Right? So both of these methods are fine.
Sure.
Okay. Also, here we go. The minus is private, the hashtag is protected. Don't worry about package private, and then the plus is public. So when you're either drawing it, you can use I'll accept minus, hashtag, and plus, or you can use these icons if you will.
Sir?
Yeah.
Can I obviously it says I can save it as a PNG, and I think
Mm-hmm.
that's how I'm supposed to submit it. But obviously, can I first add it in a Word document and add my student number and name, and I can add the code that I use for plant, then save that Word document as a PNG. Am I allowed to do that?
As long as the whole thing is saved as a PNG, then yes.
Yes, sir.
For when you submit, we are only looking for the diagram. Okay. So someone, if we're creating a UML diagram, it should be able to work. So if you save this diagram as a PNG, save image as a PNG, you should be able to give someone just this diagram and they can work with it.
Okay, but then I won't be able to submit it with my student number and name on it, or must I just name it in the file?
So it'll be all part of your zip folder, right?
So as long as our zip folder has our name and student number, then everything inside doesn't need it really.
Yes. Yes.
Okay, sir.
Because we ask you to name the files very specific things. So
Yes, sir.
inside your zip archive, you'll have a file called umldiagram.png, but your zip
Yeah.
archive will have your student number, and also the tutors will know who submitted what. Okay.
Okay. Yes,
Yeah.
sir.
Also, it's interesting to note that with plant UML, you can say this is an abstract class, and the name, the class name, is in italics. You can say it's an interface, and the interface name is also in italics. So that's just an interesting thing that they do. All right. Any other questions about UML diagrams? Let me just double check the chat and see if we have any questions. I think we're okay. So I have a question here. Yes, so it's already been answered. A class diagram is a type of UML diagram. So in UML, we actually have a lot of different types of diagrams. And let me just move this out the way. So we have things like sequence diagrams, use case diagrams, object diagrams, activity diagrams, components, deployments, state, timing, like a whole bunch of interesting diagrams. Okay. Plant UML does extra non-UML diagrams. So something like a Gantt chart is often used in project management to show like which tasks run where and what they need to do. However, some of the other really interesting ones are things like deployment diagram, where you can kind of frame cloud architectures and so on and say like where things go. But for this course and for this term, we're only interested in class diagrams. All right. So I highly recommend you have a look at plantuml.com. It's a very interesting tool for doing UML diagrams. At least for me, because you can see my drawing is terrible. All right. So let's talk about generics. We have this idea in Java, and really in Python as well, the idea of types, and that variables have types. So classes are also types in Java, interfaces are also types, like everything is a type, right? And Java is a strongly typed language, so everything has to have a clear type when we try to compile the program. Or we should be able to determine the type of something at runtime. Okay. Otherwise, Java won't let your program compile. And then Java also has issues when we try to mix and match types. However, part of this is then, if we have this great abundance of types, so we can create any of our own types and extend types, and then we have interfaces and all that stuff, how do we write things like data structures or collections that are able to use any type, right? So like we either overload the methods, with every possible type we can think of, but there are types that we might not even know of in the future, or any possible types that someone else can write So how do we write code that can kind of take that into account and use any type? And this is the concept of generics or generic programming. So generic programming is this idea that we can kind of do anything. We can have these templates, like templates that can just, when we figure out what a type is, we just sort of fill it in, right? When we need to at compile time. So you've actually encountered something called generics before, and that's when you've used an array list. And if you recall, an array list is used to store objects of a certain type. But how is an array list to know what type to use and to store and to create, right? So it uses the concept of generics, and we're going to look at the array list documentation as well as the comparable interface. But really what the generics is these angle brackets. So the thing in these angle brackets is actually the generics at work. So we have some class ArrayList, and we're telling Java that the ArrayList is getting a string class or a string type to work with. And then the ArrayList goes, okay, cool. When we create it, we again supply the type, and we can call a constructor for a new ArrayList. So what does this mean? What does this look like? Well, it looks something like the following. So we can write a generic class by specifying a generic type in the angle bracket. So when we define a new class, we typically use a single uppercase letter to denote the type, and we'll talk about some more of the conventions. And then we can just say, so a type is essentially like a little template. So a placeholder for another type, such as string or whatever class we give it, okay? And then we can do things like this. So we can declare a private attribute of the object with our little placeholder type. We can have a constructor called type wrapper with our little placeholder and then the object, and then we can do certain things, right? Like create a getter for it. And all of this while we don't actually know what type we're working with. All right, so don't worry if you don't immediately get it and immediately understand what's happening. It takes a little bit, but it's best to just think of this as like a placeholder. And it's a way for us to kind of very, very generally describe objects and describe new classes that can kind of do things. Right, so let's look at the comparable interface. Let me just increase the size here. So you can see that when we define the comparable interface, it has the angle brackets. So it's making use of generics. Okay. And you can see here that there are type parameters. And the type parameter is t, which is the type of objects that this object may be compared to. Okay. So the comparable interface, right? When we write an interface and we write the methods in that interface, whenever we give it a parameter or an argument for a method, we have to specify the type. However, now we want to write like a template for the comparable interface and say like, whatever type it is, fill it in here, right? So you can see when we scroll down, we look at the method summary and it says compared to t. Okay, so that's exactly the same as what's happening over here, except it says public, and we return, I think, an integer, and it says compared to, and then the parameter here is t. So it's just that placeholder with the other object to compare to. All right. And then we can describe exactly what it's trying to do here. So it compares this object with a specified object for order, returns an integer, a negative integer, 0 or positive if it's less than, equal to, or greater than. Okay. So when you're writing your assignment, don't worry about generics. When you're writing your assignment, we already specified that this parameter is a person. However, if you are to write like more general interfaces or general classes, you would specify a type parameter. Okay, it's the same with an array list. Sorry, let me just look over here. Array list. It's the same with an array list, except an array list, we use a slightly different notation. We have a single uppercase letter E, and E is the type of the elements in this list. And you can see that it's implemented certain interfaces, which is iterable E, collection E, and list E, right? So this is a different type of template, but it's saying I want element types, right? So E is typically used for elements. And then you can see an array list you can construct it from a collection that extends E. So any type that extends E, that kind of collection. The methods are now saying, okay, add an element, and this is the type of the element to add. Okay. So let's just look down here. I think it had another collection. Then set will take an integer index and a type called element, so a parameter of type the element that we specify. So if we go back to our example here, when we say array list and in angle brackets string, we're essentially filling in the blank and we're swapping the E here for string. So now this method signature set returns a string because E now equals string, and takes as parameters an integer index and a string element. All right. So that's the core idea of generics. It's like, let's have a placeholder for a type or an element or whatever, and then we when we get the type specified, we can fill it in, fill that placeholder in. Okay. There's also something where we can add like n, so a number where we have a type and then a number of elements. So if we have a private array like this, we can, sorry, this is wrong. So this should be either an array, or we can say like new, right, new type with n elements. Okay, something like this. So it's a way for us to specify numbers as well. So there are kind of conventions with this. When we use the letter T, we're specifically referring to a type, just in a more general sense. When we use E, we specifically refer to elements, or typically refer to elements. This is for things like collections or data structures that contain elements of a type. When we use N, we give it a number. So like if we have a capacity or an idea of like limits or constraints that we want to specify generically, we can use N for that. And then key and value is a bit like the dictionary, the idea of maps and dictionaries, where the key would be of a certain type and then the values would be of a certain type. So a Python dictionary or a hash map in Java, you would have something like the key and then the value. So you could have something like, you know, a string for the names and then an integer for the high score or the grade, right? So something like this. So that's how you would specify like a key value. Then we also have like additional types or whatever. So if you have like multiple types where it's like type 1, and then type 2 might be S, and then type 3 might be U, right? If you have 3 different types in something that you're using, you would use single capital letters as well. Right. So the big thing is that generics are just placeholders. And so we can kind of write fancy code, and then at compile time, those templates are filled in with the types that we give it. We can also infer these types. So under special conditions, we can actually leave out the second type. So with something like the array list, when we say, when we declare an array list and instantiate it, we have array list that over here now, E is equal to string, right? String, like that. E is now equal to string. The Java compiler is clever enough to figure out that this over here has to be the same as this over here. Okay, so if we're doing this where it's kind of the same type, then we can leave it out and use something called the diamond. So just the diamond notation over there. However, the age-old adage that explicit is better than implicit applies, so it's a little bit better for documentation that we know what type this is. And why do I say that? Well, if we had something like a parent class that extends a child class, we might be able to say that, okay, our parent array takes people, but when we create a new array list, we want to create them all of type children, right? And because a child is a type of parent, we can do that. So we can have this be the parent class and this be the C class, and that will work just fine, right? So that's a kind of special case where we would want to do that. If you leave out this one over here, if you leave this out and just do the diamond is going to say that this is equal to this. All right. Okay, so that was generics very briefly. There's some further reading. I would highly recommend this article documentation for the Java Standard Edition or Enterprise Edition. I would also recommend the Geeks for Geeks article. And then there are some software design patterns that might interest you. Some of these incorporate UML diagrams as well. That's it for now. I'm going to hang around. We can ask some questions, answer some questions. But otherwise, I will see you on Wednesday for kind of a post-mortem, a recap, and where to from here with Java. All right, so enjoy the rest of your afternoon. I'll stick around for some questions, some answers. I'll double check the chat, but otherwise I will see you on Wednesday. All right, any questions?
So about the courses that we do next year, about the architecture and stuff.
Yeah.
Is that more difficult than COS101?
So yes and no. If you struggled with COS101, I would really encourage you to practice programming during the holidays or before next year, just because the courses move on. So we assume that you know Python, you know Java, and that you're able to program like object-oriented stuff reasonably well. So everything builds on everything else. I will say it's about the same step in difficulty than what you had this year, maybe a bit less.
Okay.
Yeah. So I guess three things. Yeah, three things. It'll be about the same step in difficulty, maybe a bit less because you should be used to the pace and or workload of everything now and a bit more settled at university. However, it will build on everything that you learned this year and we'll expect you to know it. So once you pass this course, we certify that you know this level of things. And then 3, it'll kind of come down to how comfortable you are writing code. So I would say it's not enough to just pass the course, maybe feel more comfortable in it. Yeah.
Okay, and is it mostly Java or like Java and Python?
It depends. I think we'll continue with Java. But in future, you might actually end up writing some C++, so you'll learn C++. But the thing with new programming languages is that you now have an idea of what it means for a language to be compiled or interpreted, to be typed or not typed or whatever. So the attributes of programming languages just change, and then you learn the syntax, right?
Yeah.
Yeah. So don't worry about which specific programming languages, but practice in Python and Java. I would favor Java if you want to prepare for next year.
Okay.
Yeah. Any other questions?
No, I'm good. Thank you
Okay.
so much.
You're more than welcome.
Bye.
Bye. Enjoy your afternoon or evening.
You too.
Rest of your day, sir.
Thank you. You too. All right, everyone. See you on Wednesday. I'll stop the stream, but I'll still hang around in case you have some last minute questions.